Hey everyone, so today we're going to work on L'Hopital's rule. L'Hopital was a French mathematician and basically gives us this nice way of figuring out limits when we get an indeterminate form. So indeterminate forms would be if you get 0 over 0 or if you get infinity over infinity. Okay, so the general idea is right here. If the limit as x approaches a is indeterminate, aka 0 over 0 or infinity over infinity, then we can actually take the derivative of the top, derivative of the bottom, and take the limit as we approach a then. Now I want you to notice this is not the quotient rule. Okay, it's actually going to feel a little bit strange. You're going to take the derivative of the top by itself, take the derivative of the bottom by itself, and then try to find the limit. You can actually apply this more than once, so if you get 0 over 0 or infinity over infinity again, you can keep doing it. And again, different than quotient rule. We'll kind of talk about the rest of this as we go, but it's really nice for finding otherwise impossible limits that we didn't know how to do before. So take a look at number 1. We'll kind of jump in, do 1 through 5 here, and then take a look at number 6 as well. So number 1, it says as x approaches 0, 1 minus cosine of x over x. So as you guys might remember, the first thing we do with limits, I know it's been a while, so this will be good review from unit 1, is we try to plug in 1 minus cosine of 0, and this would be over 0. This would be 1 minus 1, which is 0 over 0. So in a general sense, we know, and maybe you would guess, that on this day of notes, we're going to talk about indeterminate forms, aka 0 over 0 or infinity over infinity. So since that's the case here, we have to use L'Hopital's rule. On a free response question, okay, an FRQ, you will have to show this work. So what you're going to do is show the numerator, what happens as I approach 0 in this case. 1 minus cosine of 0 is 1 minus 1, which is 0. And then you have to show what happens in the denominator, which is just x. If I plug in 0 for x, I get 0. You do have to write these limits, and you have to write numerator, denominator in that way. This is for an FRQ. If it's a multiple choice question, obviously they're not AP graders, they're not going to grade your work. So you can just do it in your head or plug in however you feel free. And so we're going to apply L'Hopital's rule. Okay, reason we can do that is because I got numerator over denominator 0 over 0. So what you're going to do, take this guy. We're still going to be finding the limit as x approaches 0, but I'm going to take the derivative of the numerator. Derivative of 1 is 0. And then I have minus derivative of cosine is negative sine of x divided by derivative of the denominator is 1. So all of this boils down to the limit as x approaches 0 of sine of x. What happens? Well, if we plug in 0, sine of 0 is 0. So this limit is equal to 0. Using L'Hopital's rule was a way that we could actually calculate that. Now, the rest of these are not going to be 0. So I don't want you to think, indeterminate leads to 0, etc. We'll actually get a variety of answers. It just depends on what the problem is. So take a look at 2. Number 2, we actually learned how to do in Unit 1. And we could use some algebra here. What we did was multiply by 2 plus root x. We ended up canceling. So you're able to do that still. But the nice thing about L'Hopital's rule is it's actually a little bit quicker. So we're going to try using that. Again, you have to show that the numerator, so 2 minus root 4 is 2 minus 2, which is 0. And you have to show that the denominator, x minus 4, 4 minus 4 is 0. So I get this indeterminate form. Okay, so I'm going to apply L'Hopital's rule. So you do have to show numerator and denominator in an FRQ, giving you that indeterminate form, 0 over 0 or infinity over infinity. Okay, and so L'Hopital's rule, we keep that same limit. Derivative of the top here would be 0 minus, this is x to the 1/2, so it would be 1/2 x to the negative 1/2. Divided by, this would be 1 minus 0 as your derivative at the bottom. So let's clean this up a little bit. This would just be 1, so basically it disappears. That 0 would be gone, 0 minus this. So negative 1 over 2 root x is the same thing as x to the negative 1/2. We try plugging in 4, negative 1 over 2 root 4, and that gives me negative 1/4. So final answer here If this was multiple choice, you'd find negative 1/4. If it was FRQ, you would definitely show the work. I mean, multiple choice, you might show the work as well. But FRQ, you would show that work, apply L'Hopital's, and get to that answer. All right, so take a look at 3 and 4. Number 3 we've actually seen before, and I'm curious if you remember the little shortcut we would do in Unit 1, which you're still welcome to do. So sine of 7x over 3x as x approaches 0 specifically gave you 7/3. So if you guys remember, this was the limit as x approaches 0, sine of ax over bx was always a over b. Okay, but let's say you forgot that, or you're showing work, or whatever. This is just not a shortcut you remember, and so you need to figure out how to do this problem. Again, you try plugging in 0. Sine of 0 over 3 times 0 would give you 0 over 0. You can show that work really quick. Sine of 7x, sine of 0 is 0. So x approaches 0 of 3x. 3 times 0 is 0. I get 0 over 0, so we can apply L'Hopital's rule. Okay, and the nice thing about these is we do have to remember some of our derivative rules, so it's good review. If we are going to keep the limit, okay, take the derivative of sine of 7x, cosine of 7x times 7. So don't forget about chain rule there. Derivative of 3x is 3. And we get 7 times cosine of 0. If I plug in 0, which is just 1 over 3. So we get 7/3. So notice, yes, you could have used a shortcut, and you're welcome to still remember that. If you didn't remember it, now we have a method of getting to that answer, which is pretty nice. Okay, so take a look at number 4. Try a couple more here. Number 4 is x approaches pi over 2. Again, if you're unsure, we can and the first thing you should do when you approach any of these limits is try plugging it in. So if we plug into the numerator, yes, this is the notes on L'Hopital, but you still should know that's a way to approach the problem. Cosine squared of x. This is just the same thing as saying cosine of pi over 2, whatever that number is, squared. Cosine of pi over 2 is 0. Okay, and the limit as x approaches pi over 2 of the denominator, 1 minus sine of pi over 2. 1 minus 1 is 0. So again, we get that indeterminate form. We're going to apply L'Hopital's. And reminder about derivatives coming up right here. Derivative of cosine squared. Remember, this is the same thing as saying cosine of x all squared. So you would deal with the power first, then deal with chain rule for cosine. Okay, so limit as x approaches pi over 2 would be 2 cosine of x times derivative of cosine is negative sine. So again, we deal with the power, then we multiply by the derivative of cosine. This would now be to the first power, which is why I didn't write it. And derivative of 1 minus sine x would be 0 minus cosine x. Okay, we can simplify this a little bit. This is the same thing as, let's see, these are multiplied together, so cosine and cosine can cancel. The negatives will end up canceling out. So I just end up with a 2 sine of x. And if I plug in pi over 2, 2 times sine of pi over 2 is 2 times 1. So I just get an answer of 2. All right, so that is L'Hopital so far. Again, we're checking numerator, denominator, showing our work for those limits. Might as well practice for FRQs and getting our answer. But notice the answer is not typically 0, right? Negative 1/4, 2, 7/3. So don't expect that it's going to be 0 for any reason. Okay, so we'll finish up here with 5 and 6. 5 is kind of fun because it has a lot of derivative practice in it, and I know that's what you were looking for, so we'll get to do it. Again, you can assume that it's going to be L'Hopital in this case, but you still would do the same thing, which is attempt to plug in 0 and see what you get. So 6 times 2 to the 4 times 0, so 2 to the 0th. This would cancel to be 1, plus 2 times cosine of, oh, I'm sorry, I probably should write, before I plug it in, I really should write just the numerator. 2 cosine of pi minus x minus 4. Okay, then I'm going to take away the limit because I'm going to actually plug in 0. So 6 times 2 to the 0th would be 1, plus 2 times cosine of pi minus 0. Cosine of pi is -1, and then minus 4. So this gives me 6 minus 2 minus 4, which is 0. Okay, how about that denominator? Limit as x approaches 0 of tangent of 2x. Tangent of 0 is 0. All right, so 0 over 0, we're going to apply L'Hopital's rule. And this is where it gets fun. We have to remember some interesting derivatives here. Okay, so let's try it out. Limit as x approaches 0 of, so denominator maybe is easier here. Tangent of 2x would be secant squared of 2x times 2. The top we have, okay, so 6 would just chill outside. Don't try to combine it with the 2. That's algebraically not correct. 2 to the 4x, remember for anything like a to the u, okay, it's a to the u, if I took the derivative here, a to the u times ln of a times u prime. All right, so we're going to get 2 to the 4x itself times natural log of 2 times derivative of the exponent is 4. All right, plus 2 times derivative of cosine is negative sine. So I'm actually going to write this as -2 sine of pi minus x. And this is also going to be times -1 because of chain rule. All right, what else we got? Minus 4, well, that's just plus 0. This guy would cancel with the derivative. So if we want to rewrite this a little bit, or we could just plug in 0 and kind of see what happens. The numerator here, we would get 6 times 2 to the 0th. So this cancels to be 1, times natural log of 2 times 4, minus 2 times, actually it's going to be plus. I'm going to multiply these negatives together, if that works. So it's going to be plus 2 sine of pi minus 0. Sine of pi is 0, so this whole thing cancels. All over secant squared of, well, 2 times secant squared of 0. Secant squared of 0 would be 1. So let's see. 6 times 6 times 4 times natural log of 2 divided by 2. So this gives me, I'm sorry, I'm running out of space here, 24 natural log of 2 over 2, which is 12. Natural log of 2, final answer there. Okay, so I think that one's kind of tough just because it has a lot going on with derivatives, but take your time on it. And again, this is a good time to reflect on chain rule, reflect on some of those top 15, or not top 15, but derivatives you should definitely know for AP. All right, and number 6 is going to be the last one we try together. So take a look. Okay, it says here is f of x. Let g of x be differentiable. It gives you g prime. We also know the limit of g of x is infinity. So we want to find this limit of the fraction. So we want to find the limit as x approaches infinity of f of x over g of x. Okay, so what we'd want to do here is first kind of find each one. So what happens as we approach infinity for the numerator, and what happens as we approach infinity for the denominator. Okay, reason for this is that's kind of how they gave us the information. Also, we might be thinking this is L'Hopital. So it tells us right here, this guy is infinity, okay? And then f of x is given to us right here, 2x plus, I'm gonna write this 3 over e to the 5x. So think about it this way, guys. Negative exponents flip to the bottom. So it would be e to the 5x in the denominator. The 3 would just stay on top. Okay, if we were to plug in infinity, now I know you can't really plug in infinity, but think of if you plugged in a really huge number, you would get 2 times infinity, a huge number, plus 3 over e to the infinity, so some big number. So this is 3 over, trillions. This whole thing, this is going to dominate. This is going to go to 0. So basically what you end up with is huge number plus 0. That's going to be equal to infinity. Okay, and we have infinity here. So what do we got, guys? Infinity over infinity. So we're going to apply L'Hopital's rule. Okay, so let's finish up with that. We're told about what G prime is. We can find F prime on our own. So I'm going to actually shrink this down a little bit, and I'll show you what we're going to do next. Okay, so since we're going to apply L'Hopital's, we're going to do limit as x approaches infinity of F prime of x over G prime of x, which is, okay, F prime would be 2, I'm reading right here, okay, 2x would be 2 plus 3 e to the negative 5x times negative 5. So don't forget about chain rule there for that exponent. E to the u is itself, and then times u prime, divided by, let's see, so I'm going to rewrite this as negative 15 if that's okay with you guys. So it's 3 times negative 5. So now I have this, and I may rewrite it one more time. Stick with me here. I'm going to rewrite it like this. Okay, so 2 minus that. Denominator is given to me right here. I'll highlight it in purple. G prime, 1 over x plus 4 cosine of 5 over x. All right, so we're going to plug in infinity, hypothetically. So I want you to think about what's going to happen. This is good review because it's a little bit abstract. Back to unit 1. So this would give me 2 minus 15 over e to the infinity. Again, this would dominate, so this thing would go to 0. Okay, then I have 1 over infinity. Again, this would go to 0, plus 4 times cosine of 5 over infinity. That inside would go to 0. So I really have 2 over 4 cosine of 0. Cosine of 0 is 1. So final answer, 2/4, aka 1/2. So after all that work, final answer here, guys, would be 1/2. You know, this could be a section of an FRQ. That would be the work you're expected to show. And that's about it. So we'll try 7 and 8 when we are in class. And let me know if you have any questions. Thanks for watching.